Hi, this is Mrs. Often. I'm here today talking about transformations of functions. So we have 6 basic functions that you've probably worked with before. The linear function, y equals x, absolute value, y equals the absolute value of x, the quadratic, y equals x squared, the cubic, y equals x to the third, the square root, y equals the square root of x, and the basic rational function, y is equal to 1 over x. So the first thing we're going to look at is the horizontal and vertical shift. This shifts a function to the left, right, or up or down. If I have a function g of x, and I have it that it is equal to the parent function f of x minus h, something happening in parentheses, plus k, this function has moved right h units and moves up k units. You'll notice that this is kind of backwards thinking. Well, it's minus h, but it moves to the right. Yes, if it's plus h, it would move to the left. So you change what's inside the parentheses. What's outside the parentheses, that plus k, stays the same. So if it's plus a number, moves up. Minus a number, moves down. And I put here, remember, you should only change if you're inside. So I want to graph the function g of x equals x minus 3 squared minus 1. So I think my parent function is that quadratic function. Looks kind of like this. My g of x graph is going to move right 3 and down 1. So I'll take this 1, 2, 3 units to the right and down 1. And apart from that, it's going to look just about the same. So you see it looks the same shape. What's changed is its shift. So let's move on to another type of transformation, and that is vertically stretching or shrinking the function. This is making the function stretch taller or made shorter and wider. We do this by multiplying the function by number a. If a is greater than 1, we end up with a vertical stretch. If the absolute value of a is in between 0 and 1, this is a vertical shrink. Now I've put the absolute value of a here for a reason. We'll see more about this in the next slide. But in our first example, we're graphing g of x equals 2 times x to the third power. This really isn't going to make a whole lot of difference. Okay, I look at this. A equals 2. So its absolute value is greater than 1. I'm going to stretch that graph taller. My parent function, the cubic, looks like this. It's not going to shift left or right at all, but instead of going up 1 and over 1, I'm going to go up 2 and over 1. And then because this goes down 1 and over 1 on the other side, I'll go down 2 and over 1. What you've noticed for this function is that it looks narrower because it's being stretched vertically. I kind of think of Procrustes, if you've read the Odyssey, who would stretch out his travelers if they didn't fit onto his special bed that he had prepared. Not a very nice guy to go visit, I would say. After a vertical stretch and shrink, we want to consider other things we could do with a. So g of x is equal to a times f of x. What if that a value is less than 0? Well, we can still look at the absolute value of a and think, does this stretch or shrink? But if a is less than 0, f of x is reflected in the x-axis. So it flips it upside down. In this example, I've combined 2 things in my quadratic. I have negative, so it's going to get flipped, and 1/2. Here, a is less than 0, And the absolute value of a is in between 0 and 1. So that means that this graph is going to flip upside down and get wider. I'll just draw a quick sketch of the parent function for a visual reference. And then here, again, starting at the origin, going down 1 and over 2 units on each side. So down 1 and over 2 again. And my function has been flipped upside down and appears slightly wider due to this 1/2 coefficient. This is called the leading coefficient, by the way. All right, and our final transformation, one that fortunately we don't see all that much of, but it is important anyway in trigonometry especially, is reflection in the y-axis. Here I have g of x equals f of negative x. What does that do? But it reflects the function in the y-axis. Notice that the negative sign is now inside the parentheses rather than being a coefficient multiplying the parent function. So it's part of the argument of the function. For some functions, such as the absolute value function or the quadratic function, the graph of the opposite of x will look exactly the same. So here, if I take my original absolute value graph and I reflect it in the y-axis, it looks the same. So I have what's called an even function. On the other hand, some functions may look different when reflected in the y-axis. An example of this is the square root function. The square root of negative x, normally my square root function would look like this. But now it's been flipped, it's pointing the other way. This is also called an odd function. So sometimes this reflection in the y-axis is important. Okay, and our final slide asks us to put this all together. I have a square root function here, a lot of stuff going on. I notice that this has a shift. The negative 3 is going to make it go to the right 3. The positive 2 is going to mean that it moves up 2. Will this graph be stretched taller or will it be shrunk, shorter? Well, I look at my coefficient, that negative 2. The absolute value of negative 2 is in fact greater than 1. So this is going to be stretched taller. Then I want to ask myself about reflection. Will this be reflected in the x-axis, in the y-axis, or in none of the axes? Looking inside the square root sign, I see that this is not negative x, so it's not going to be reflected in the y-axis. However, my leading coefficient is negative, so when a is less than 0, that gives me reflection in the x-axis. So overall, my graph is going to go right, up, it's going to flip, and then be stretched. And that's how we put together the transformations of functions. Thanks.